Aerospace engineering is broken up into two different main branches, aeronautics and astronautics, which have their similarities and differences. Aeronautics has to do with building and designing things that fly in air, whereas astronautics is about building and designing things that will go into space, which is the focus of this video. For many schools, you would simply enter as an aerospace engineer, then you diverge into the astronautics or aeronautics classes later on. So astronautics would include designing rockets and satellites, or specific things like working on the International Space Station, which is basically one big science lab in space that astronauts stay and perform experiments in. Or maybe the Mars rover that is gathering data from Mars without the need for a human to be there. Now, rockets are made in order to launch space shuttles and satellites into space. Then, for example, those satellites are used for a variety of things, including providing television signal to our homes, taking high-quality images of Earth, forecasting weather, locating our position through GPS satellites, taking scientific data about our land, oceans, or atmosphere, or even for military purposes like reconnaissance, or communicating securely with our troops halfway across the world. In fact, there are over 2,000 satellites currently in orbit, so you can see how astronautical engineering is an important and active field. Now, like I said, astronautical engineering is a branch of aerospace, but within that branch there are many components that you would focus on even more. Remember, spacecrafts are really big, so it takes a lot of people, all with different specialties, to create one. Some of the common subsystems and components I'll cover are propulsion, structure, thermal, attitude determination and control, guidance and navigation, and communications. Now, propulsion, of course, has to do with the propulsion system on the spacecraft that provides the thrust. There aren't too many propulsion methods, but it's all about knowing when to use one over the other and accounting for all the little details. For example, launching a rocket uses a solid fuel, kind of like gunpowder, which is a powerful type of propulsion to overcome gravity on the spacecraft. But if the spacecraft is in orbit, you might need it to change to a different orbit, so you need to determine what propulsion and how much of it is needed to provide the change in velocity that you want. Or in deep space, one method you could use is electric propulsion, which is weak but very efficient. Other details would include shaping and determining the material for the nozzle, sizing the tanks that would hold the fuel, and figuring out how much thrust a certain method could provide. Then structures is about designing the structure of the spacecraft, so actually how it is shaped and how it will stand up to all the forces it's subject to. As you can imagine, just when a rocket is launching, there are lots of vibrations and heavy stress that occur throughout the vehicle, so it's important that everything is designed properly to withstand that. This is also a subsystem that you could see an astronautical or mechanical engineer working on. Thermal is about maintaining heat and temperature properly throughout the entire spacecraft. For example, the electronics, batteries, antenna, and maybe even the people inside the spacecraft need to be kept within a certain temperature. Some components may need to stay colder than others or they will malfunction, so understanding how heat moves throughout a spacecraft is very important. This is something that you could also see an astronautics or mechanical engineer working on. Attitude determination and control is all about controlling the orientation of the spacecraft. Think about the fact that you have to aim a remote control at or near a TV to turn it on. If you just turn or orient it a different way, then it won't work. Well, the same thing goes for a spacecraft orbiting Earth. It may have an antenna on it that has to point at something on Earth to communicate with us. If along its orbit it turns too far, then the antenna may not be able to communicate with what's on Earth, just like the remote control couldn't communicate with the TV. Well, we can mount sensors on the spacecraft that detect when its orientation begins to turn too far. Then we can use devices to provide a torque to get it back to the required orientation. In classes, this involves a lot of looking at coordinate systems and different axes to determine how a spacecraft is oriented mathematically. Guidance and navigation is all about designing the orbit itself, or really just planning out the mission of how the spacecraft will travel. You may need the satellite to be geosynchronous, meaning it takes one day to complete a trip around Earth, so you gotta look at what shape orbit you should have. Or if at some point you just need to change between orbits, the team would have to determine how much change in velocity there needs to be to do so. And lastly, communications is about wireless communication, so that maybe two satellites can communicate with each other, or a satellite can communicate down to a ground station to provide information, whether it be images, sensor data, or audio from someone talking. I only included communications because at some schools, aerospace students may learn some of it, but usually in the real world, this would be best for probably an electrical engineer or similar discipline. So you may really want to work on rockets and other spacecrafts, but it's not that simple because as you can see, there are so many parts of a spacecraft that need to be included, and people sometimes spend an entire career on just one component or subsystem. Now, plenty of engineers work on spacecrafts, from astronautical engineers to computer scientists and computer engineers who need to create the software that will go on board. But as you can see, astronautical engineers work on the bulk of the spacecraft itself. But what's really nice about this major is that if maybe you don't like propulsion, let's say, that's okay because there are plenty of other subsystems you can work on so that you wouldn't even see propulsion in your career. And additionally, if you really like one subsystem, you could spend an entire career on it. Now, if you did want to work on the entire spacecraft, you could get a job as a systems engineer. These are aerospace engineers that know a little about all the components and subsystems instead of being an expert on one. This is kind of what undergrad will prepare you for. They will teach you about all these different subsystems, but won't go into too much depth. Then in your career, or maybe graduate school, you could go into much greater detail on one of the subsystems you find interesting. Now there are some more that I didn't include, like risk and reliability, safety, testing and integration, and some others, but these aren't so much taught in the undergraduate curriculum, but just note how many parts of a spacecraft you could work on if you wanted. So to summarize everything so far, a spacecraft is comprised of many subsystems and components that need experts in each one of those fields. The ones in green that I'll write are what undergrad will focus on the most. Some schools may briefly go into communication and power, which is why I put them in blue, but not all schools will, and if those interest you, then electrical engineering will be better for you. Systems engineers have to know a little about all these subsystems, which is kind of what school prepares you for, like I discussed. But if you want to design the next breakthrough in propulsion, let's say, that will get rockets to much faster speeds, then you'd probably get a master's degree where you'd focus on the propulsion subsystem. Or you could work your way up at a job where you try to focus solely on the propulsion system itself rather than the other ones. Now your curriculum will be very similar to a mechanical engineer. You will learn a little about everything, including fluids, thermodynamics, circuits and electronics, material science, programming, as well as take about 2 years of calculus. Also, a little more than half of your aerospace engineering classes will be the same as the aeronautics students. You both take a lot of the same major classes. But then you diverge into the astronautics classes where you learn about many of the subsystems discussed earlier. So you will see plenty of math and labs, but also be ready for a lot of MATLAB. I've talked about this briefly before, but for those who don't know, MATLAB is a program that has a lot of math functions built into it that allows graphing in 2 and 3 dimensions and allows you to mathematically model a lot of systems by coding what you need. Like maybe you'd have to model the position and velocity functions of a spacecraft in orbit around Earth. Think of a graphing calculator, but way more advanced, and you will have to do coding to model what you want. So if you're thinking aerospace engineering will just be hands-on and won't be a lot of computer work, you will be surprised when you enter undergrad. Now lastly, some people may struggle between choosing mechanical and aerospace engineering. If this is you, just realize they are very similar in what they do when it comes to the technical work. They both learn thermodynamics, they both analyze the forces and stress within different structures, they learn material properties, they use MATLAB, they do a lot of math, and so on. But astronautical engineers only apply those things to spacecrafts. Then they also go on to take their classes in the subsystems shown earlier that a mechanical engineering student would not see. So mechanical engineers do have a wider range of options in the job market because they could look at the temperature and heat transfer on a car engine as well as a spacecraft. Or they could analyze the forces on a robot or large building as well as a rocket. Astronautical engineers will have more of an advantage when it comes to working on things like the attitude determination and control, the propulsion system, or the orbits, and the other subsystems that are more unique to a spacecraft.